Welcome to 8 lectures on terpenes and terpenoids. In this lecture, we are going to discuss about the chemistry of gingiberine molecule. We will see the occurrence as well as uses of gingiberine. We will discuss the structure of gingiberine on the basis of chemical methods of analysis, and at the end, we will discuss about the synthesis of gingiberine. The major source of the gingiberine is ginger. It is used as cosmetics as well as fragrances. Gingiberine shows various medicinal properties such as antiviral, anti-ulcer, and it also shows anti-fertility effects. It is an optically active compound and it exists in the levo form in ginger. Now let us discuss the structure of gingiberine on the basis of chemical methods of analysis. Earlier days, the chemists were not having sophisticated tools for structure determinations, and therefore they were relying on the structure determinations of gingiberine on the chemical methods of analysis. In chemical methods of analysis, generally this gingiberine is isolated in a pure form from ginger, and after isolation it is subjected to series of chemical reactions. After each chemical reaction or after each experiment, they were deriving some conclusion about the structural features of the gingiberine molecule. Here, this chemical methods of structure determination starts with the determinations of molecular formula. So carbon and hydrogens of the gingiberine is estimated, and then they reach to the molecular formula of the gingiberine, and it was found to be C15H24. This molecular formula is a very useful information about the structure of gingiberine molecule. It contains 15 number of carbon atoms. It means that there are 3 isoprene units, and these 3 isoprene units are joined through head to tail according to the special isoprene rule. Now since it contains 3 isoprene rule, it means that gingiberine molecule belong to a class of sesquiterpene. Now apart from this broad idea about the presence of 3 isoprene unit in gingiberine, we also get information about the double bond equivalence or a degree of unsaturation in gingiberine. Double bond equivalence or a degree of unsaturation means how many double bonds gingiberine contains and how many rings it contains. Double bond equivalence is calculated by the formula x plus 1 minus y by 2 for a molecule CXHYOZ. So if you keep these values here, the degree of unsaturation in gingiberine is found to be 4. Now 4 degree of unsaturation in gingiberine may correspond to the presence of 4 double bonds in gingiberine, or it may correspond to the presence of 4 rings in gingiberine, or it may be the combinations of double bond as well as rings in gingiberine. So in the incoming investigations, we have to find out the nature of this unsaturation. Degree of unsaturation is equal to 4, and we have to find out the nature of this unsaturation. So let us see what are the chemical reactions or experiments to investigate the nature of unsaturation. The first experiment is the hydrogenation experiment. Gingiberine is subjected to hydrogenation in presence of platinum catalyst, and we get here C15H30, and it is called as a hexahydrogingiberine. So if we subtract the molecular formula of the gingiberine from the hydrogenation product, we find that 3 molecules of hydrogen are left. It means during the hydrogenation, gingiberine has consumed 3 molecules of hydrogen. So 3 consumptions of 3 molecules of hydrogen confirms that gingiberine contains 3 double bonds. We already proved that there are 4 unsaturations in gingiberine, double bond equivalents. Now out of 4 unsaturations, 3 unsaturations are due to the presence of 3 double bonds in gingiberine. So we got a very important information just by hydrogenation experiment, the presence of 3 double bonds. Now 3 double bonds in gingiberine molecule may be conjugated or may be non-conjugated. So we have to find out the nature of these 3 double bonds. And for that the second experiment is performed where gingiberine is subjected to sodium metal dissolving reduction using sodium in ethanol. Metal dissolving reduction is a characteristic reaction of the conjugated system. For example, it responds to the butadiene, it responds to the alpha beta unsaturated carbonyl system. It also responds to the aromatic system called as Birch reductions. Gingiberine also participates in a metal dissolving reduction, and here we get dihydrogingiberine reactions. This reaction was carried out in the year 1913. So the formations of dihydrogingiberine clearly indicates that here out of 3 double bonds, the 2 double bonds are conjugated here. Now additional evidence, this fact that out of 3 double bonds of the gingiberine, the 2 double bonds are conjugated is further supported by its reactions with HCl. When gingiberine is treated with the HCl, it forms dihydrochloride derivative. We already said that two double bonds are conjugated, so HCl reactions with the butadiene forms 1,2 addition as well as 1,4 butadiene 1,2 as well as 1,2 or 1,4 addition products, and the another isolated double bond will form the hydrochloride derivative, and therefore in this way we get the dihydrochloride derivative. So from this experiment, these three reactions, it is proved that gingiberine contains three double bonds, and out of three double bonds, the two double bonds are conjugated in gingiberine molecule. Now let us make some chemical arithmetic again. This hydrogenation product C50H30 is a completely saturated molecule, and C50H30 corresponds to CnH2n, and CnH2n corresponds to here presence of one ring here, and therefore hydrogenation product since corresponds to CnH2n general formula, it means that gingiberine molecule is monocyclic in nature. So we have progressed a lot as far as the structure of gingiberine is concerned. We have proved that it contains four double bonds, four unsaturations. Out of four unsaturations, there are three double bonds. Two double bonds are conjugated because it responds to metal dissolving reductions, and there is a presence of one ring here. It is monocyclic in nature. So four unsaturation, that is three double bonds, and the one monocyclic corresponds to 4 degrees of unsaturation. Now again, let us find out few more evidences in support of the presence of two conjugated double bond. If it is a conjugated, then it must participate in a Diels-Alder reactions, and therefore it is observed that gingiberine molecule forms an adduct with the malic anhydride, and the formations of adduct with the malic anhydride clearly supports our observation that two double bonds in gingiberine are conjugated. Then ultraviolet spectrum, UV spectrum, if you record of gingiberine, then the lambda max value is at around 260 nanometer, and 260 nanometer is a definitely characteristics of the homoannular dyne type of the feature present in gingiberine molecule, because the fundamental the base value for the homoannular dyne is 253 plus. Plus means here some ring residues or some substituents are there. Accordingly, some increments are there to the basic 253 value here. So for homoannular dyne, according to Woodward-Fisher rule, it's a 253 plus. For heteroannular dyne, it's a 214. And since the value is very high, it's a 260 nanometer, we assume on the basis of lambda max is equal to 260 that gingiberine molecule is a homoannular dyne. So in this way, we have proved that there are three double bonds in gingiberine. Out of three, two are conjugated, and it is monocyclic in nature. And this monocyclic nature contains the two double bonds which are homoannular in nature. This is a homoannular dyne. Now after this, let us find out the positions of these functional groups. We have to find out the positions of these three double bonds in this entire skeleton of the gingiberine molecule, which also includes presence of one ring. And for that, ozonolysis experiment is a turning point of investigation. When gingiberine is subjected to ozonolysis, it forms three products. One is acetone, then this dicarboxylic acid, and here we get a lavulic acid. Now the formations of lavulic acid as well as this dicarboxylic acid and acetone, similar ozonolysis products were obtained by the ozonolysis of bisabolene. It was the year 1925, so before the structuralization of the gingiberine, before the ozonolysis of gingiberine, chemists were having some literature support from the ozonolysis of bisabolene. And bisabolene exists in alpha form, beta form as well as a gamma form. Alpha bisabolene, beta bisabolene and the gamma bisabolene, and the common skeleton of these three is can be written in this way. Now since ozonolysis product of gingiberine are very much similar to the ozonolysis product of bisabolene, we can assume that gingiberine is having a skeleton of the bisabolene, and therefore one can write a tentative skeleton of bisabolene in this way. Now in this skeleton here, the formations of acetone, this skeleton is supporting to our ozonolysis reactions because acetone is formed, and therefore the positions of one double bond we have assigned here in this way. Now the positions of remaining two double bonds we have not assigned here, and for that we have to do some more experiments here. Now these two double bonds are conjugated, it is a homoannular system, and therefore there are three possible structures of the gingiberine molecule. It's a homoannular diene, this is also homoannular, and this is also homoannular diene. Now out of these three possibilities, there is only one structure of the gingiberine is possible, and for that we have to give some evidences. Now this evidence, this experiment is a turning point of investigation to reach to the structure of gingiberine molecule. One double bond position we have already assigned, we have to assign for the positions of two double bonds here. Now for that, again, gingiberine molecule is reduced in presence of sodium in ethanol, and we got dihydrogingiberine molecule. Now this dihydrogingiberine molecule contains two double bonds because butadiene is converted into one alkene here, and the isolated double bond is not reduced by sodium in liquid ammonia. It is not reduced by sodium in liquid ammonia. Therefore, this is the nature. This dihydrogingiberine contains two double bonds, and these two double bonds are oxidized by KMnO4 to form the keto dicarboxylic acid. Here there is a loss of three carbon atoms. Three carbon atoms are lost in the form of acetone here, and the resulting compound is a keto dicarboxylic acid. The analysis of this compound has shown that it's a dicarboxylic acid. It contains a keto group by just preliminary functional group analysis, and its nature was found to be keto dicarboxylic acid. Now this keto dicarboxylic acid responds to bromoform reaction, sodium hypobromide, reactions with sodium hypobromide NaOH plus Br2, and the bromoform reaction is a characteristic reactions of the methyl ketone. We are getting one less carbon atom. It is lost in the form of CHBr3. Bromoform is formed as a side product and is converted into carboxylic acid. So we get now here another tricarboxylic acid. Now in this experiment, if we get the structure of this tricarboxylic acid, keto dicarboxylic acid, then one can reach to the structure of gingiberine very easily. Now let us focus on this. Let us focus on this tricarboxylic acid. Out of this three carboxyl group, one carboxyl group will be definitely due to the cleavage of this double bond. Here we will get a COH molecule, and the remaining two carboxylic acids are due to the oxidation of is is due to the oxidations of the methyl ketone. It's a methyl ketone this is already having a dicarboxylic acid here. So this structure of this tricarboxylic acid was found to be this one, and this is formed by the haloform reactions, and therefore the structure of this keto dicarboxylic acid was found to be here is a methyl ketone. This on reduction, this on oxidations with sodium hypobromide forms a tricarboxylic acid. Now this product is formed by the cleavage of carbon-carbon bond, and therefore since it's a methyl ketone is formed in this reaction, it means that this methyl group is present on the double bond here. So one can write the structures of the dihydrogingiberine. This is the product formed due to the cleavage of this ring. This ring is here, and this ring is cleaved now to form the keto, and it's a carboxylic acid. So the positions of the double bond can be written in dihydrogingiberine in this way, and this product is possible only when we assume the structures of gingiberine here written like this in the box. So with the help of this experiment, we reach to the structures of the gingiberine molecule. And once again, let us see how this experiment works. A gingiberine reacts with sodium, and we get a reductions of this double bond. It's a conjugated, and we get a dihydrogingiberine. Now these two double bonds are cleaved under oxidative conditions, and we get a keto carboxylic acid from this, and one carboxylic acid acetone is lost, and that's why there is a 12 number of carbon atom here, and later on it responds to the haloform reaction, and we get a tricarboxylic acid. So this is a turning point of investigation as far as the structures of the gingiberine is concerned. Now once gingiberine structure is proved, let us see here Diels-Alder reactions. We have said that it participates in a Diels-Alder reaction. It forms an adduct, and similar reaction is reported in the literature in 1950. Gingiberine can be rewritten in the form of a butadiene format. Butadiene reacts with this acetylene here, and we get here bicyclic system in a reaction called as a Diels-Alder reaction. And this Diels-Alder adduct undergo a retro Diels-Alder reactions under reflux conditions. On heating under pyrolysis, it undergoes retro-Diels-Alder reactions, and we get here methyl 4-methyl phthalate. This is a dimethyl phthalate and it's a 4-methyl phthalate. In this way we are getting. So this reaction again proves that gingiberine molecule contains two double bond and which are conjugated to each other. So we have reached to the structures of the gingiberine molecule on the basis of very preliminary reactions. We started with the hydrogenation. We have done here reduction with sodium in ethanol, and here dihydrochloride derivative, how it is formed. See here, one can assume this HCl will be added here, and one can get here 1,4 additions of HCl, and that's why the dihydrochloride is formed here. Then its ozonolysis gives us acetone, this levulinic acid, and this dicarboxylic acid. Similar results were obtained from bisabolene. KMNO4 oxidation and then followed by haloform. Haloform reactions gives us a clue to put a double bond attached to the methyl group, and that's why since we have kept a double bond here, it is possible only when we assume the structures of gingiberine in this way. This is a Diels-Alder reaction just we have discussed earlier. Now let us see here how this lambda max value is calculated in gingiberine molecule. The observed value here is 260 nanometer and the calculated value here is a 268 nanometer on the basis of Woodward-Fischer rule applied to gingiberine. The base value for humanular is 253 nanometer, and there are three increments. Here is a 1, 2 and 3 increment, and these are the increments for alkyl substituents or a ring residue, and these substituents for one is 5 nanometer, and therefore we are having plus 15 nanometer. So this is a expected value is 260 nanometer and the observed value is 260 nanometer. It is close agreement, it is somewhat close agreement, and therefore again it proves that gingiberine molecule is a conjugated molecule. Now in gingiberine molecule contains here two chiral centers, and since it too contains two chiral center, it is an optically active compound. The naturally occurring gingiberine is in the LEVO form in ginger. Now last one here is about the synthesis of gingiberine. Synthesis of gingiberine gives an additional evidence for the structure of gingiberine. There are 15 number of carbon atoms here, and 15 number of carbon atoms are assembled through the reactions of here methylheptanone. Methylheptanone is offering here 8 number of carbon atoms. This is providing 6 number of carbon atom. So 8 plus 6 is equal to 14, and one carbon atom is provided by the methyl magnesium bromide. So we get here this methyl substitute. This is coming from Grignard. This ring is coming from aromatic system, and this one is coming from methylheptanone. Here very basic reactions are involved, and that's why this synthesis of gingiberine is very interesting to discuss. Methylheptanone can be formed from ethyl acetoacetate chemistry. Ethyl acetoacetate forms here acetone, is a substrate. Acetone can be prepared from ethyl acetoacetate, and we have already seen its synthesis in case of geraniol as well as citrol. So we will not discuss more about it. Now this methylheptanone is treated with the Grignard reagent, and total we get here total 14 number of carbon atoms, and then this ring is reduced in presence of Birch reduction, sodium in ethanol. So this is a applications of the Birch reductions for the synthesis of natural product like gingiberine. So there are two important methodologies. One is a Grignard reaction and the second one is the Birch reductions, and on the basis of this one can reach to the synthesis of gingiberine molecule. So here we start with the Grignard reagent, paramethoxy phenyl magnesium bromide is treated with the methylheptanone. We get this tertiary alcohol. Tertiary alcohol undergo dehydrations. We get this double bond conjugated with this aromatic system. It is reduced. This double bond is reduced as well as this system is reduced, and we get a vinyl ether type of the moiety here. And this vinyl ether under acidic conditions undergo rearrangement here, undergo hydrolysis, and we get a cyclohexenone. Cyclohexenone treats with the methyl magnesium bromide, and we get a 1,2 addition here, and tertiary alcohol is formed. And tertiary alcohol undergo dehydration in presence of oxalic acid, and we get here a double bond. In this way gingiberine is formed. So we have completed the discussion on the structure determination of gingiberine as well as the synthesis of gingiberine, and here very simple experiments are performed, and therefore I hope you have understood the structural relations of structures of gingiberine as well as the synthesis of gingiberine. Now, once we have prepared this, we have discussed this. Now it's time to talk about the possible questions on gingiberine molecule. The first problem is related to the degree of unsaturation here. Hydrogenation of gingiberine gives hexahydrogingiberine. Calculate the hydrogen deficiency and hence the number of rings present in the molecule. This problem gives us an opportunity to revise the fundamental of calculating the degree of unsaturations, and it's correlating to the presence of ring here. We have already discussed in the previous slides. The another variety of the problem is related to the experiment. Here experiment is given, and from the experiment the student is supposed to derive the conclusion. Molecular formula, from molecular formula what are the possible information. Hydrogenation experiment gives you what kind of the information. So all this we have discussed in our previous slides. So students should undertake this kind of the problem to convince themselves regarding the chemical methods of structure illustrations. Now this last slide is related to the Woodward-Fisher rules, calculations of lambda max applied to the gingiberine molecule. It's a homoannular dyne, and therefore students should undertake the applications of Woodward-Fisher rules applied to the gingiberine molecule. And last one here is about uh, haloform reaction, and some burst reductions involved of gingiberine molecule. So dihydrogingiberine is formed, then it is oxidized and it responds to the sodium hypobromite, and we get here tricarboxylic acid. The molecular formula of the intermediate products is shown. So students should undertake this kind of the exercise to convince themselves about the chemistry of gingiberine molecule. So we have completed this gingiberine molecule, and gingiberine molecule is a belonging to a class of cis-quaterpine. Farnesol also belongs to a class of cis-quaterpine. We will, in the next lecture, that is lecture number 9, we will discuss about the santonin molecule, which is also belong to a class of cis-quaterpinite. Thank you very much for watching this video. Subscribe the video, like the video, and stay tuned with chemistry. Thank you very much.